Today we are going to continue with the whole background behind neural networks. So this is very extensive and yeah, but I always try to take the time to drill into it because it's very good to understand the basis on which the current AI technology of today is built. So we are going to continue. We've already looked at neural networks and we've also understood the fact that neural networks were basically just implementations of a mathematical logistic regression. That's what a single neuron is, right? And it initially was considered to be, similar to how the brain neuron functions. And in a way, you could draw the analogy, as you can see on this slide that we're kicking off with. We've already seen this slide, but I want to start from here. And so we have an analogy, even though it's not perfect, because the human brain is a bit, in fact, not a bit, far more complex than what we currently use as the mathematical model for a neuron. But the human neuron, the animal neuron has a bit more things. But in a way, you could draw those similarities. So we have seen how um, the inputs, right? Basically, think of it as a single neuron is a unit that represents a single regression model, a logistic regression model. So as it encapsulates that single mathematical operation, it becomes easier for us to think about. And when we now bring multiple neurons together, we can now see how they behave. We can have an understanding behind it. So yes, that's what a neuron is. It's an activation function F that is applied to the sum of the weights and some of the product of weights and inputs into that particular neuron. And then, of course, the bias. So that's the model. This is still another representation of that same model. You have the inputs coming in, then you have the weights. So you have the weighted sum, x1 times w1 plus x2 times w2, and so on all the way till xn times wn, all added up together. And then the bias, which you can see the bias as a weight that has an input that is always one, right? So all of that is added up. And then you have the activation function. So we talked about activation functions as well, and the different types of activation functions. And the fact that an activation function brings about a nonlinearity that is very much needed, very much a part of the model. Without that nonlinearity, we would not be able to solve, nonlinear separable problems. Effectively, you would not be able to build a function approximator for nonlinear functions using neural networks. Okay, so we also talked about layers and what makes layers more powerful. Of course, with a single neuron, you cannot still solve a nonlinear problem. You cannot create a nonlinear decision boundary because a single perceptron or a single neuron is still a linear model, right? But when you combine layers, that means you are stacking them. Not only are you stacking them, you're also combining them in parallel. So a layer is a parallel combination of neurons that are each operating independently, right? And each has its own weights and bias and its own output, but they all receive the same input vector. So they all will see the same input, and the weights will determine how each neuron responds to that same input. So while they all get the same input, they don't all respond the same way to that same input. And that's what really makes layers very powerful. That's what makes a layer effectively a feature engineering system. Because what happens is when one neuron takes the same set of inputs, but it has its own different set of weights, right? So it's going to interpret those inputs differently. Another neuron in the same layer that's in parallel takes the same set of inputs again, but it has its own different set of weights. So its own interpretation of the input will be different, and so on and so on and so on. And you continue that, for all the neurons in that layer. So what you end up will be a new set of outputs from that layer that is different from the set of inputs. The vector of inputs that came in will be different from the vector of outputs, for each data sample that comes in. So what's happening effectively is that after you have trained a multi-layer stack of neurons, you can end up with each layer. Uh, you can consider that each layer has learned how to feature engineer, basically identify what matters, at each layer. So we talked about the types of layers, the input, the hidden, and the output layers. And the input layer basically just takes the whatever signal comes in, whatever data comes in, whatever features, and you now have one neuron per feature. The input layer doesn't typically have trainable parameters, so you cannot train it. It just takes the input and then it forwards it to the next layer. And the next layer is the hidden layer. So the hidden layer is where all the learning really happens, where all the feature engineering really happens, where all the knowledge representation really happens. Because in the hidden layer, and there can be many of them, in most deep neural networks, you have lots of hidden layers. Typically, you could have hidden layers. In today's modern neural networks, you could have hidden layers of up to 1,000 hidden layers, right? For the really big networks. Okay. Others may have maybe smaller numbers, hundreds. Smaller networks would have maybe 50, maybe 10, maybe 20, depending on what problem you are trying to solve. So that is where the magic really happens, right? Um, that's where the magic really happens. So it is in the hidden layer that the magic really happens, and it's quite interesting. Okay, so now when we talk about hidden layers, there are two key things, right? Like we said, the first one is the fact that each of the neurons in the hidden layers um, effectively um, represent a new, one of a new set of features, right? So by training each of them, each layer becomes a new feature set. And you can make the neurons in hidden layers much more in number than the original input features. That way you can end up engineering a broader feature set. You can also make it much less, and therefore you can end up engineering a narrower, a smaller feature set. And that second piece is what is quite interesting, because what that means is that you can effectively use your neural network for dimensionality reduction as well. Because what's going on is you can then train the neurons, and then maybe the final few layers you make them to have much less features, and you have effectively reduced the dimensionality of the original data. Okay, but it's probably not as it can be used in some situations, right? But it's probably not as efficient or performant as the ones we've talked about, because you have to end up training an entire deep neural network just for that. So that's the first thing, the fact that each layer is a new set of features. It's feature engineering. But the second thing is that every layer becomes better and better, right? In learning about the data sets that you have given to it. to learn. So effectively, each layer um, begins to extract much more nuanced information, much more nuanced relationships in the data. Okay. But more importantly, at the end of the day, when you stack layers, you now transcend that limitation of a new single neuron can only is a linear model, so it can only solve linear separation, linear decision boundaries, problems that have linear decision boundaries. But when you stack a second layer, it becomes nonlinear, especially when you include the activation function. And that's what the activation really does. It bends, it folds, and it reshapes that input space. So the neural network can then learn nonlinear decision regions. Then the Apple layer, the main purpose of the Apple layer is just to take the knowledge that has been learned and represented inside the model and, you know, put it out in a human recognizable format. That's basically in a format that, relates to the original data that was given to it. So that's really its purpose, to produce a final prediction. So typically that means the number of neurons you have in the output layer depends on what you're trying to predict. If you're trying to do a binary prediction, binary classification, you only need one neuron. If you are doing a categorical multi-class prediction or classification, then the number of neurons will match the number of classes that you have. If you're doing a linear regression, you only need one single neuron because regression, so if you're doing a regression problem, whether it's linear or whatever, or even more complex one. That is, you're trying to predict values. You only need a single neuron that will predict that value. And typically, the activation function is also task dependent. So if you're doing classification, you're going to use either sigmoid for binary or softmax for multi-class. And if you're going to do a regression where you want to predict a single value, then you're going to use a simple straight through linear activation function. Basically, you are just passing the signal straight through. So that's it. And now we now talk about different types of layers. So we've talked about layers from the standpoint of where they are in the stack, right? Input, hidden, and output. But we also have layers in terms of the interconnectedness of the inputs and the neurons. So the very basic one that we talk about is a dense layer or a fully connected layer. So a dense layer or a fully connected layer is a layer where every input is connected to every neuron. So this is a good example of it. So you have this as the three inputs, right? And then each of these three inputs is connected to each of these four neurons in the next layer. So you have the input layer here. Then you have, each of these three is connected to this one. And each of these three is also connected to this one, and so on. So you notice that because of that, the next layer will always have three inputs because there are three inputs up here. So there'll be three here, there'll be three here, there'll be three here, there'll be three here. While the previous layer will always have four outputs because there are also four here. So you have four, 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 right? That's a densely connected. But we also have the converse, which is sparsely connected. So the sparsely connected is not guaranteed that every single input is connected to every single neuron. So in this case, you can find that some of them are missing. Like here, it's connected to only two of the three input neurons. This one is connected to only one. This one is connected to only one. This one is connected to only two. Right. So the numbers here are not stable. So in sparsely connected, typically what happens with sparsely connected, since each connection actually is represented by the weight, if the weight is zero, that means just think of it like there's no connection, right? So a sparsely connected network is a network where the weight matrix, some of the values in the weight matrix is zero effectively. So some of the weights are zero. So what that means effectively is that, for example, for this case, this neuron, the weight from this input here is some positive or negative value, some non-zero value. Here is also some non-zero value, but the weight between this and it is zero. And you look at that, that's what is called a sparsely connected. And that's what makes it sparse, that you have zeros in the weights matrix. That's another way of looking at it. So the mathematical form, this superscript here represents the layer. Okay, so you see something like ZL, Z for the current layer equals weight for the current layer, right? Weight for L times A. A is the output of the previous layer. So you can see this L minus 1. So it's the output from the previous layer, or the activation from the previous layer. So remember we said when you're talking about neural networks, we typically use the letter A to represent the output, not Y. Y is normally used for the final output, which is from the output layer. From hidden layers, we use A to represent intermediate outputs, basically, so activations. And then we use the superscript L to represent the layer that we are currently dealing with. So Z, which is the internal state of the current layer, would be weight, which are the incoming weight, times activation, which is the actual value of the neuron or the input, for each, for the previous one, plus the bias, right, for that layer. So that's it. WL is the weight matrix, BL is the bias vector, and AL is the previous layer's output or activation. So what's a feed-forward network? We now put all of these ideas together. A feed-forward network is network where information or data or signal flows in one direction. It's always going forward. So typically the characteristics of a feed-forward network is one, data flows in one direction. So when you're solving for this network, for example, you start by calculating the input into the input layer. Then when you have solved for all the inputs here, you now essentially feed forward. That's what feed forward means, right? The signal is fed forward to the next layer. And then from the next layer, you'll be able to also calculate the inputs into it, because you already have the inputs as the output from the previous layer, and then the weight. So output times weight. Remember, the input layer just passed the inputs through, right? So there wasn't any specific operations here. And then the hidden layer here takes each of these inputs, multiplies by its weight, and gets an internal Z value, and then the activation function is applied, and that forms the output. So in that same way, each of these neurons in the hidden layer will get an output that's calculated the same way. And then the output layer will receive each of these outputs. There's also weights, that connect each of the neurons in the hidden layer to the output layer. All right. And then that output will now again do a weighted sum and get its own internal state. And then that internal state, you pass it through the activation function and you get the output, right? And then when you get that output, of course, the output you get is a predicted output. So you also have the actual output, which is the data that you want to learn from. And from there, of course, you calculate the error, which is the difference between the predicted output and the actual output, right? That is what we call the loss. Okay. So it's the same principle that we have been using all this while. The only difference is that you are doing cascaded calculations, right? The signal comes from inputs, goes through the input layer, goes through each neuron, in each hidden layer, layer by layer, and then it finally gets to the output layer. And that's it. So each previous layer fits into the next layer. There's no cycle of feedback loop. That's the most important differentiator in a feed-forward network. That's why it's called feed-forward. There's no feedback loop where you have signals flowing back from the output or from a succeeding layer back to a previous layer. There's no such reverse direction of signals. That's what makes it a feed-forward neural network. And the feed-forward is essentially the foundation of modern deep learning. Modern machine learning with neural networks, basically. Well, that's deep learning. Perceptrons were feed-forward networks, even though they're single. And then we have what we call a single-layer perceptron, a multi-layer perceptron. A feed-forward network is both. And like I said, you know, at each layer, the input enters the network. At each layer, you have the linear transformation, which is the weighted sum. the WIXI, right, for each I, and then the activation function, and then the output. So this animation kind of gives an idea of what is happening. So you see that each output, each neuron in the next layer receives input, the same input. And this allows you to correlate this to the matrix because what's going on is actually matrix multiplication. And that's why we were talking vectorization. Vectorization is essentially a way to represent matrix algebra by using symbols this way. So you don't need to remember every single number or position in the matrix. You only need to think about the entire matrices or each matrix as a single entity, right? And then you can do all the matrix operations. For example, this is a dot product. So the multiplication of the weights by the input signal is a dot product. As the input signal is passing through um, the weights, right? They are attenuated. So you are going to have the WIXI, right? The summation of WIXI. And the way you can understand it as a matrix is if you look at this, the weight is typically a matrix where it is for each row represents the output, right? Each row represents the output, each of the neurons on the output. The the weights combination, right? This matrix in the next layer. Let me not say output, right? It's on the output of the previous layer, but let's say the matrix, the um the neuron in the next layer. So the neuron in the next layer is connected to N. So there is this convention which we use. Let me bring up the convention just for ease of explanation. If you have a simple, let's say a simple setup like this, where you have, let's just look at a very simple setup where you have three inputs neurons, right? In the input layer, three neurons in the input layer. Okay, and you have just one neuron in the next layer, which is the hidden layer. And you now have, if it's fully connected, so you have this connection going that way. Okay. Now, this relationship here can be represented as a matrix, as a single matrix. So let's break it down. So first of all, um, each of this is the weight. It represents the weight of, so let's call this W. So this is the W, and typically you would, um, let's call this, let me use the right nomenclature, the right um, notation, so as to make it easy to follow. This W is the weight that is connecting this input to this output, right? So you could call it W, let's say 0. It's going to be a bit but let's just call it W00. Okay. So the W00 here, what this means basically is that this weight has is connecting the zeroth um input with the zeroth output. Okay. So let's assume this is let's call it A0, which if you look closely at the animation, that's what you see. So this is A0, this one is A1, and then the next one is A2. So those are the three that you have. This one is A2. Okay. On the same layer. So the layer is 0. I'm not going to do the layer But if you look closely at this, you see that you have A0 with zero above. The zero above means the zeroth layer. So all of these are one layer. That's why the superscript is going to be the same number, 0. While this one is on the second layer, so it's going to be 1. So for now, A0, A1, A2. So the weight that connects A0 to this A0, this is another A0 too, right? It's another A0 too, but the A0 here is A0 on the second layer, okay? So that's why we have a second superscript to confirm or to disambiguate, because effectively this one is A0, 0. I think we could do that as well. I could say, okay, this is A0, um, 0, meaning that it is A0 on the first layer, right? A1, 0. That is A1 on the first layer. And then A2, 0, which is A2 on the first layer. The second, the third input in the second layer. Then this will be A01. The second number is a superscript. Basically, it should go up and be in brackets. So ideally, this should actually be in brackets if you want to go by that convention. Okay. So, yeah. So with this, now, what you notice is that A0, W00 is the weight that, that is connecting the output from A0 on the first layer or the 0th layer to the input of A0 on the next layer. Okay, that's W00. In the same way, this next weight here will be W01. Um, that will be W01, while the third one would be W02. So that's the weight that is connecting A2 to W0. So the interesting thing is if you pay attention to this convention, you will notice that the first number in all of this W0, this 0, that the first number is referencing the destination. That is the first number 0 here, they are all 0, right? W0, 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 then 1, 0, 1, 2. So it's all referencing the fact that this is connected to the first output or the first in the hidden layer. So that's one thing that I think is sometimes confusing when you're asking this convention. Is it actually the weight from 0 to from here to here? Because you would have said this should be 0, 0. Yes, that's correct. But this should have been W10 because it's connecting A1 to A0. But that is not how it's interpreted. Rather, it's interpreted as W01. That is, it is connecting A0 backwards. So we look at it from the standpoint of A0, from A0's view, as if you are at A0 at this neuron and you are looking backwards. So W00 is, or W0 would be connecting W00 will be connecting A0 to the 0th one, W backwards. Now, that's kind of the putting it in the matrix. You know that we now put it as a single row, right? Those three weights now get put in a single row. So what we are saying is that we use these three weights to map this inputs, these three inputs. Remember, the inputs are features. So we take this, each input is a feature. So what we are saying is that we are using this three weights to map these three inputs, okay, to this single output. And these three inputs are three features. That is how the mapping is. So you see how it moved. And that's basically what this animation is saying, that all of the weights, right, that map this. So you can think of it this way, that this weight is mapping this input to this output, right? This weight is mapping this input A10 to the same A01 output, while this third one is also mapping this. So maybe a better way to draw this would have been something like this. Let's stack it up. Let's stagger it. Staggering it makes it easier for us to see, right? That and then we can put this here. So staggering it allows us to see that each of these is just allowing you to do a mapping. Okay. And then the third one allows you to, so we are essentially saying each of the weights allows you to map the input through the weight to this output, input through the weight to the output. Remember when we're doing feature engineering, each feature was in a column. In that tabular structure, each row was a data point or a sample, while each column was a feature. So that is why A0, A1, and A2 are stated in columns as features, right? They are stated in columns as features. They're not stated in rows by the side, but at the top. While interestingly enough, the output is stated by the side as a row. So this is now the arrangements. So this is a tabular arrangement saying we take each of these ones, 1, 2, 3, right? And then we do that sum. So remember that sum that we talked about. And so that's it. We do that weighted sum. We will sum when we multiply. So remember, this is a product, by the way. A0 to W0 plus A0 times W1. Sorry, A0 times W0 plus A1 0 times W01 plus A2 0 times W02. And that answer is what will form is 01. Of course, you pass it through the activation function. So the next set of weights, if you had maybe another, let's say you had another output, like here. Let me draw it down here. So if you had another output that is down here, okay, then you see that let's say you have another output. And this output also has its own connections, right? Because it's fully connected. So each input is going to connect to that next one, the next layer, right? So this is now going to be mapped as another set, but it will be mapped here. So you're going to have a W0 again, but this time, sorry, W1, because the W, remember the first letter always represents which neuron on the output or on the next layer. So it'll be W10 plus W11 plus W12, right? And this is going to give you the next neurons output, which is A1 on the next layer, which is layer 1. Okay. So that is the mapping. I'm just trying to explain the mapping of this graphical display to the matrix. So you can now see that we have two rows. I can actually remove the plus sign because, oh, I can remove the plus sign because we don't really need the plus sign, right? So I can remove the plus sign and we'll just look at only the numbers. And that's when you will now understand that it is really just a matrix of weights. The weights are just a matrix. And you can just keep adding more for each new output or for each new output from the previous layer or inputs, from the previous layer, you would have a new um, row like this. So if we had like five, like in this case, if you look at this example, this animation, you have one, two, three, four, five, six. We have six. So that means we should have six rows here. One, two, and so on till six, right? Then for each of these, they will still map to the same number of features that are coming in, the same number of neurons are coming in from the previous layer, right? So the number here, one, two, three, four, five, six, seven, eight, actually maps to the number of columns here, and that goes all the way to X. So then what you now ask is, what is this vector? This vector is a signal that is coming in or the input. In this case, we are taking the input from a single data point. That's why it is a vector. If you are taking the entire data set, then this will turn from being a vector to being a matrix. And that's why we do transpose, right? But here it comes in as a single vector. So let's just say a single data point. So that single data point, you now have a matrix multiplication. So if you go and check out the maths of it, you find that when you do a dot product, which is take this row, right, and multiply by this single column, which is what this animation is showing, you now get an answer, which is the output from this single neuron. So the output from this single neuron is all the inputs from the previous layer times all the weights, going into this neuron from that times all the weights. So that's a dot product. Of course, that is what is in this bracket. Then there's a bias which is added. Of course, the bias is part of the a parameter, and then all of that is added and then passed through the sigmoid function or whatever other activation function you have, and you end up with that. So this is kind of showing you the transformation of this graphical representation of a neural network to the mathematical representation, right? Or rather, let me put it this way, the graphical representation of a single layer and the forward propagation, you know, from this graphical representation, we map it to a matrix multiplication operation. So anytime you see that that gives you the understanding that neural networks are basically matrices. And it also makes sense because remember, we said the model for a single neuron is a weighted sum. So by the time you take this is a single weight and this is a single input. By the time you take this and do a dot product, it will be W00 times A0 plus W01 times A1 plus W02 and so on. And that would take you to the value of this one, which is a weighted sum. That is the Z, right? Everything, this dot product is the Z. So that's kind of the breakdown of this. So typically, yeah, the input enters the network, then each layer applies that linear transformation. And that linear transformation is a Z, which is a weight matrix, right? Multiplied by the input vector or matrix, as the case may be, plus the bias, okay? And then that Z is now passed through the activation function F. That gives you the A, which is the activation for that hidden layer. The final layer then produces a prediction. So what's actually going on in a neural network, in a deep neural network, is this thing that you're seeing, but across multiple layers. This is just one layer. The other thing is that while this calculation is being shown kind of sequentially in this animation, but in real life, all of the calculations for a particular layer are typically done in parallel. Well, maybe not exactly in parallel, but they are highly parallelized, right? Not all may be done at the same time in parallel. They that really depends on the capacity of the GPU and the computational you know um, um, the computational system or tool that is being used for it, right? So at the end of the day, this is the same thing as you doing a calculation. When we're saying predict, we did that function def predict, right? Where you define a function and you did a forward calculation. That is what forward propagation is. It is the prediction step of the network. Like I said, unlike when we were doing linear regression, logistic regression, and all of those, where it was just a single calculation, here it is a multi-step calculation, right? Where each step corresponds to each layer. So if you have 10 layers, it's going to be 10 steps, right? But the good news is that all those 10 steps will be handled for you. So we'll go look at how the layer by layer mathematics is done and the tooling that helps to do that. So from the input layer to the hidden layers may be more than one, maybe multiple, and you also still have that iterative, stepping through each layer to the output layer. That's how the signal is flowing, and that's what we mean by forward propagation. Okay, so this is still another animation, except this time there is no matrix, right? This is just showing you graphically. So the interesting thing here that you learn is that neural networks, there are at least two ways you can represent them. You can represent them graphically this way, because it is now a unitized mathematical operation, right? Or it's a, a set of complex mathematical operations that have been unitized. So you can see each of them as a single unit, right? And inside each of these, there is a single linear regression going on, or logistic regression going on. And if you do all the calculations for a single layer, right, at once, it becomes a matrix equation, because it's a system of linear equations. That's what a matrix is, right? If you remember in those days when you take a simultaneous equation, what we call simultaneous equation, which is like two or three equations, that's essentially what neurons are. Each neuron represents a single equation in a set of simultaneous equations. So if you have three neurons, that means you are solving three simultaneous equations. And you remember how we would break down three simultaneous equations into a matrix multiplication between a 3 by 3 matrix, depending on the number of parameters or the number of coefficients, and so on and so forth. So that's basically what is going on here. Now there is also back propagation, but we'll talk about back propagation later on. Forward propagation ends with the output. The output is the y hat. Then the y hat, you compare it with the original data, the true data, what it's supposed to be, and you calculate the error. Same thing we've been doing all this while. So in the same way, this is just another visualization of the same thing. Each layer transforms the input into a higher level presentation. Yes, higher level in the sense that each layer engineers more features, higher level features, better features, right? And this is the same formula where the internal state of each neuron is the weight times the activation of previous layer, right? Again, this is the entire matrix. So this, when you see these uppercase letters, it's referring to the entire matrix. So it's referring to the entire layer. The calculation is all of the matrix in that layer, which basically a matrix represents, okay? Plus the bias, and so on. So again, this is still another representation of the same thing. Again, still with some animation as well. So still the same thing, for each layer, the forward propagation, this is the intermediate state, right? Before the activation. Weight of that layer times X, which is the input flowing into that layer plus the bias for that layer. Then you apply the activation. Here, a specific activation is mentioned, the ReLU, which we talked about, rectified linear unit activation. And that's it. So when this is computing the first layer, right? This first layer. And then this is computing the second layer. So the second layer, you now see that the superscript is 2. So the number above is 2. That means layer 2. So layer 2, you still take the weights of layer 2, the weights that connect layer 2 to layer 1. That's the W2. and you multiply it by the activation of layer one, which is the previous layer, right? Plus the bias of the current layer. And then you apply activation again. This time around, you use a sigmoid because this is like the output layer. Okay. So this is if you were manually calculating for each, maybe you had a simple single layer perceptron and you are manually calculating the output using this. So this is how you calculate it effectively. You have the input layer x1, x2. So this x1, x2 forms the matrix X, right? And then the weights form the matrix W. And you have the bias and you calculate the Z. You pass it through a ReLU and that gives you the activation. So this is the output, right? From that hidden layer. And then um, the output from the hidden layer, the A, now becomes input for the output layer, which is layer two. So you have Z2 and then W2 plus B, which is the bias of layer two, which is the output layer. So you get the Z2, which is the intermediate state, intermediate value. That Z2, you now pass it through a sigmoid, which is this symbol here, and you get the Y hat. So remember, the output layer is sigmoid. That gives you the Y hat. And the sigmoid is used for a single class binary classification, effectively. Okay, so let's look at a bit of a recap of loss functions. This is not different from what we have already looked at when we're talking about loss functions. Loss functions are basically um, they allow you to calculate how far your network's predictions are from the true values or the true labels. Okay, so it's the same as any other training that we have done before. The purpose is to guide learning during training. It provides a quantitative error signal, which you use for optimization and training. And the intuition is normally if you have a smaller loss, that means your model is predicting better. If you have a higher loss, then your model is not predicting very well. So the loss becomes the objective function that you want to minimize. So training a model is all about minimizing the loss. That's what it has always been. And the different kinds of loss functions that you will use depending on the different tasks, like we have seen already. Regression task would use mean square error. That penalizes large errors and outliers. We've gone through this already. Binary classification, you use a binary cross entropy, BCE. This works with a sigmoid curve as the output. For multi-class classification, use categorical cross entropy, which works with a softmax output. And then these are the equations. We've already seen this again. So for mean square error, the loss is the mean 1/n, which is what will give you the mean, times the summation of y hat minus y squared. You know, summation of the squares of the errors between the predictions of each sample in your data set. You take the mean. Binary cross entropy, this is a bit less intuitive to understand, but in a way, you remember I said it's a piecewise combination of how far away my prediction is, you know, when it is true, which is this, and how far away when the real value is true, plus how far away my prediction is when the real value is false. So that gives you times the real value, right? So that gives you a measure, the a largest measure of the your prediction, how close it is to what it's supposed to be. So of course, because we're using log values here and the predictions are typically in the range of 0 to 1, the logs will be negative. So we have to use a negative sign to bring it to flip the sign and flip the curve into the positive side of the graph. But we're still going to take a mean value of this. So it's still divided by 1/n of the sum of the negative log likelihood of each data point. Then for categorical cross entropy, you will now do a different thing. Instead of essentially categorical cross entropy is a generalized form of this binary cross entropy. Because if you look at it, what we are basically doing here, we are taking the yi for each class where C is the um, C is the number of classes. So if you reduce this to where C is 2 for two classes, you find that it reduces to yi log y hat I, right? Plus yi2 log y hat I2, right? So you are going to have um, you know, two components to that sum, which is what this is, right? The only difference is that here we have flipped it so that we get zeros when we are closer to zero. So for categorical, it's a more generic form of this same binary cross entropy. You are just multiplying the logit by the real value or the true value. So you have the true value yi multiplied by the log of the predicted value, which is the probability. Okay, you multiply it for all the classes in that category. So if there are four classes like red, yellow, blue, green, this log term, there will be four of it. Just like for this binary, we had two log terms here, but here we'll have four log terms. And then this is for a single sample, and then you add that again for all the sample points. Again, because it is log, and we are summing everything, we are going to end up with a negative number. So we have to use a negative sign to eliminate that and flip it. And that's the loss function. So let's look at back propagation. So what is back propagation? We just talked about forward, feed forward. Feed forward means the signal is going forward from the input to the output, which is pretty good. It's the prediction phase or the inference phase of a model. But one of the biggest challenges, of course, one of the key elements of machine learning is being able to train your model. Being able to train your model, one of the key elements is being able to calculate the updates to the parameters or weights. And how do you calculate the updates? When we're doing simple linear regression, simple logistic regression, those can be considered as a single layer in a neural network. They're equivalent to a single layer. So it's easy for you to calculate the loss. From the loss, it's easy for you to calculate the gradient. Then from the gradient, it's easy for you to calculate the updates to each of the parameters, right? And of course, you apply the learning rate to that gradient and you calculate the update. Now, but the question is, in a neural network where you have multiple layers, what do you use as the loss for the previous layer? Because if you think about it this way, when we are doing a single, calculation, right? You have your loss, so you can calculate the loss here. It's very easy, right? This is the output, and it's easy for you to calculate the loss, from this. The loss is here, the y hat here, and you can easily calculate the y minus y hat, right? Y or y hat minus y, whichever one. At the end of the day, you have to, you know, adjust for the sign. So this is very straightforward, right? You calculate the loss y minus y hat, and then you take that value, right? You now calculate the gradient, which we have seen the ways to calculate the gradient. We use there's a gradient function which you can use. Typically it is take this y minus y hat, which we call the residual, and multiply it by the signal x. So here you would have a signal x, for example, and then to calculate the gradient, which is a backprop, which is the effect of this effect of the parameter to the output in the reverse direction when you're training the model, we typically do this. Of course, it becomes very easy because it has been proven. It's been mathematically proven. We now do x, dot product of y minus y hat. Okay, where y minus y hat is what we call a residual. So that's all nice. Okay, for a single layer. But the problem that arises with neural networks is, what if I have a second layer now? I now have a second layer here, okay? I want to calculate the gradient, backwards. What happens? That was an unsolved problem for a long time because here it's easy for you to calculate the gradient of X of this loss with respect to this. But if I'm going back to preceding layers, it becomes more difficult. How do I calculate for a parameter in a previous layer? How do I calculate the width, the impact on the width, right? How do I calculate it? It becomes a bigger challenge, and it wasn't solved for a while in the early days. In fact, it is because it wasn't solved that is why neural networks were not very prominent, right? That's why all we had in those days was a single layer perceptron. A single layer perceptron was basically a neural network that had only one layer. So it was easy for you to calculate the weight updates, right? Which basically is effectively just um a linear, a logistic regression, right? Model. So this issue of how do I calculate the gradient here? I didn't draw this well, but this question of how do I calculate this gradient here was a really tough, difficult question to answer. And nobody really answered it very well until these two gentlemen whose picture you are seeing. They decided to tackle that question. All right. Um, and the history of it is that um, researchers have been working on that problem. How do we solve it? How do we calculate the gradient in the second layer? Yes, we know the gradient in the first layer, cool. But how do we solve the gradient in the second layer? This is a problem that researchers worked on for many years. This problem, how do we calculate this? What is the mathematical equation or function that I would use to calculate this? And because we are not just calculating the influence of the previous layer. We're not calculating the influence of this previous layer on the parameters of this, um, sorry, the, the influence of the layer ahead on the parameters of the layer that is previous to it. We are calculating the influence of the output itself, the whole output, right? Not just, we are trying to calculate the influence of this. This is what we're trying to calculate. The influence of the cost function itself to a parameter that is way, way, way behind. In fact, you could even see in some other deep neural network architectures, they could even have even more layers. And the question is, I am at this layer, right? And this layer has a parameter W here. And I'm trying to calculate, right? How does the y hat that is far ahead, in the future, or far ahead in the stack, what is the influence of this loss, this y minus y hat? What is the influence of it to this w that is way back here? This was a big challenge mathematically. But yeah, these two gentlemen worked together, one after the other. One started and then the other one kind of finished it. They developed what we call the backpropagation algorithm. So a backpropagation algorithm took several decades to develop by several researchers across different fields, right? And it was used in so many other in solving other kinds of problems. But the first researcher that looked at that approach and clearly described it as something that can be used to solve neural network, this problem of how does how does a loss function affect this particular parameter that is way, way, way at the back of the stack? That was this Paul Werbus in his 1974 PhD thesis. And then later on, two other people, David Rumelhart and Geoffrey Hinton, right? And Ronald Williams popularized it in their influential paper in 1986. And that is how backpropagation came. And backpropagation became a game changer for neural networks because effectively it means you could train deep neural networks, multi-layer networks, because you could figure out those layers that are far, far in the middle or far, far at the back, right? You could figure out how to adjust their parameters in a way that the network is actually learning, in a way that is responsive to the loss that is way, way at the, end of that stack, in a way that is responsive to the gradient of the loss, in a way that is proportionate to the impact or the effect of that particular weight or parameter to the entire, um, you know, output of the entire network, right? So that was the beginning of modern neural network research because it essentially said, hey, we are no more limited by perceptrons. We can now have multi-layer neural networks. So we can now solve the exclusive OR problem. We can now train those networks using backpropagation, right? And gradient descent didn't come as at that time, but backpropagation at least showed a way to propagate the gradients backwards. Okay, so the limits, there were still limitations from not having sufficient data and computational constraints because backpropagation, even the forward propagation and backpropagation require a lot of computational capability. And those were not very much available in those days, right? Um, so it was limited. So yes, the algorithm was discovered, but its usage was still limited. And it's part of what contributed to the AI winter, which I talked about when we started this course. That there was periods, several periods in past history where people lost interest in AI. And there was no funding for research and there was no talk about it for a while, simply because it was not meeting up all the huge hype and expectation. So again, that just tells us AI is not today that AI started having a large hype, you know. So anyway, in the more recent years, from the year 2000 forwards, we started having improvements in computational power, right? Especially with the advancement of GPU technology, graphical processing units, graphics cards, and then the internet also um, became the powerhouse that, or the data house. From the internet, a lot of people began to engage, and a lot of data came out from people's engagement with the internet, websites, Wikipedia, social media, all kinds of things that essentially became the source of data. So there was a lot of data in the thousands. So that unique combination of growth of computational power and data availability due to the internet and several other things led to the backpropagation algorithm becoming more capable or more useful in training neural networks. And eventually that led to the resurgence of neural networks. So from the 2000s, has just been up and up and up, and the rise of neural networks. So the idea behind backward propagation is that it computes the gradients of the loss function with respect to each network parameter. That's what, of course, that's what we are trying to do, right? So that we can know how much to adjust each parameter and in which direction, right? Following the principle of gradient descent so that the model learns. Okay. If not, your model is not going to learn anything. So it uses a principle of the chain rule in partial differential equations. I'm not going to go into that, but the chain rule basically says that if you have 10 different variables that influence a particular variable, 10 different variables on the input that affect a particular variable on the output, that you can get the proportion of each of those 10 variables, how much it contributes to the change in the variable by doing a partial differential, right? Just look at only the effects, just look at how much the overall variable would change if you did a small change in this one. So it's kind of saying it is there are rules for it, right? Like I said, I'm not going to go into that, but it's partial differentials, which is calculate the gradient of this parameter with respect, or sorry, calculate the gradient of the output that is contributed to by all the 10 inputs, but calculate the change with respect to only one input. And that change is a partial differential. And it's enough to define, that this is how much this one contributes. So you don't need to look at the other nine. You just look at that one. And then when you're done with that one, you look at the next one and so on, right? So it's a chain rule. It's if you have a two variable thing, it is something like u dv dt plus v du dt equals the total contribution, right? Something like that. And that's product rule. So so you use the chain rule. Okay, so that's product rule, but the chain rule is yeah, let me state that the chain rule is saying the effect of a stack. Um, let me put it. It's saying if you have a stack like this, where you have the output, this output depends on this, and then this one depends on this. Okay, so the chain rule says something like dy dx equals dy dy z times dz dx. That is a chain rule. So I think I mixed that up with the product rule. The chain rule is saying something like you can actually break up a relationship into chains, you can chain it. And let's assume, let me just do a quick let's assume that we have an output here, and this output is the y hat, or let's just call it y. And then this y, this intermediate one has an output a, right? So let's say um let's say a2, while this one is a1, right? And this one is a0. So you are saying this is the intermediate um this is the intermediate uh, output for this hidden layer. This is the output for this hidden layer. This is the ultimate output. Then remember we said something like in um dy dA, the A0, right? This will be saying the impact of A0 on Y, which is what we're trying to look for. We want to calculate the impact of A0 on Y so that it is that impact that forms a gradient. And that's what you use to adjust A0, like what we have been doing with linear regression, except that now we are crossing multiple layer boundaries, right? It's a multi-layer boundary. We are not just doing, what we did before was just dy dm or dy d, yeah, we did dy dm or dy dc and so on. So it's kind of the same thing, but this time around we are saying for me to find the impact across this, we would have to get the gradient of all intermediate values. So that would be dy dA2, right? Times the A2, the A1, times the A1, the A0. So basically we are saying the impact of A0 on Y, or the impact that Y is getting from A0, is the product of the impact that Y is getting from A2 times the impact that A2 is getting from A1 times the impact that A1 is getting from A0, right? That is the chain rule. So you are chaining the impacts, basically. And the other interesting thing is that even within the cell, within the neural network itself, a single neuron, you also apply that same chain rule to something like this, where you could say dA, right? dx, where x is the input. So x, remember, is the input into a particular neuron. while A is the output from that neuron. So the A dx would be the A dz, right? Remember, Z is the intermediate um, value times dz dx. So dz dx is a standard linear dz dx that we did. In fact, if you go check out our logistic regression, you find that this is kind of what we did, right? While the dA dz is the activation function. Remember, the dA, A is activation function applied to Z. So dA dz is actually a gradient of the activation function, while the Z dx is a gradient of um, the intermediate value Z with respect to the inputs, okay, which is effectively the weights, right, um, of at that point. So this is kind of a chain rule. It's a bit more involved than this if you want to go into the depths of it, but I just wanted to mention that. So backward propagation is effectively just a chain rule, right? And you use the differentials, which are the gradients, to calculate for each weight or parameter. So the amount of the total network loss that each parameter contributes to is calculated based on that chain rule, and then you use that amount to update the that particular parameter. Of course, you still use a learning rate on it. So that was the foundation, or that is the foundation of backpropagation, and that really was a revolutionizing thing that you know improved the ability to use neural networks. And so that's that. Today we are doing backpropagation. We don't really do backpropagation by hand anymore, right? It's something I used to do some time ago. Um, because we have a lot of tools and frameworks that have that all built in. So we are going to look at that. So the forward pass, if you are doing back propagation, you first do the forward pass, which is to compute the prediction. That's step one, like what we have always done. Then step two, you compute the loss, again, like what we've always done. Then in the backward pass, you compute the gradients. So this is a new one. For previous training that we've been doing on the basic linear regression and logistic regression and all the rest, the backward pass was just calculate the gradient. You were just calculating a single gradient of dy dx, or dy dm, rather dy dm, dy dm1, dy dm2, or whatever, right? Dy hat dm1 or dy hat dm2, dy hat dc, which we're calling dm, dm0, dm1, dc, whatever. Those were just gradients. So it was just a single gradient. But with back propagation, we will now use chain rule to calculate the gradient for every single parameter all the way back to the parameters at the beginning, right, of the stack. Parameters here will calculate their gradients. Parameters here will calculate their gradients, but for this one, we use chain rule from here. All the parameters here as well in this layer will calculate all their gradients, but we use chain rules from here, which is coming from chain rules from here, and then all the way back, right? So that's why it's called back propagation. Basically, propagating the gradient calculation backwards from the output layer all the way back to the input layer. So it's in the reverse direction to the forward propagation. And as you are calculating, when you are done calculating, you can then update the weights of each of the layers, basically parameters, right? So those are the key things. Number one, the back propagation relies on the chain rule. Number two, the activation is very key because the activation is a non-linearity. If not for activation functions, if we had just the linear um uh transfer function, a linear activation function, then it would simply just be a single logistic regression, a single linear regression, right? But the activations can determine gradient flow because the activation determines the threshold and which elements get a piece of the gradient and so on. And then the other thing is we now have what we call a vanishing and exploding gradient. The reason for that is because it is multiplicative. Since the chain rule is multiplying, if those gradients are small and you're multiplying small numbers with other small numbers, you get really small numbers that can become very low, right? That is vanishing gradients. But on the other hand, if the gradients are also large, when you start multiplying large numbers, multiple large numbers, you start getting very large numbers. So you can also have your gradients exploding. So typically you find that the gradients at the close to the beginning of a neural network stack tend to be very large or very small. That is what we mean by vanishing or exploding gradients. But there are ways to solve that. Okay, so what I explained, this is kind of a visualization of it, right? So for a weight W in any layer, the update is new. This new is a learning rate. So this is now another new symbol for learning rate. We've used alpha and we've used LR, but now we're using new. And then del L, del W, this is the partial differential, essentially the chain rule, and the partial differential, the change in the cost function with respect to this particular parameter. But for you to calculate the change of the cost function with respect to this particular parameter, you need to backpropagate it. So this tells you how that is done. You start from E, which is the um, cost function at the output, right? The E, the W, this is still the same thing as the cost function, two different symbols, but meaning the same thing. And then you have the W11. So we want to see the effect that this weight has on this particular error or cost function. For you to get it, you have to go backwards, step by step. So you take the one with respect to A1, right? The E1, the A1. E1 is this one, the A1, right? Which is the output from this. And then you multiply A1 with Z1, right? And then you multiply the Z1 A1Z1 for layers 2. Then you do the same thing for layers 1. Okay. A1Z1 of layer 1. So you see it kind of cascades that way, right? The Z1, the A1 of layer 1. Then you add to it this other pathway as well because it also contributes through this other end. So that's where the plus comes in. You have two pathways, right? So the back propagation goes through this pathway and it also goes through this pathway. So that's why you have two terms in that chain rule. So you have the first chain rule, which is 1, 2, 3, right? For this pathway, and then the second for this pathway, which is again 1, 2, 3. So that sums up to the contribution that this weight has to the output. And this is kind of a summary of that. It's just saying the gradient flow for each layer L, right? The weight of the layer ahead of this current layer, transpose it times the error. So we're now using this um symbol. This um this is delta, right? The delta symbol for the error. So you are taking the weight of the layer ahead. You transpose it, then you multiply by the error, which is essentially, yeah, the cost of the layer ahead as well. And then you multiply that, or you have a product of that with the gradient of the um, cost function. Sorry, the gradient of the activation function. F is the activation function. So the gradient of activation or derivative of activation function is F prime, right? By that. So again, this is a lot of maths which we will not need to bother about. We will not need to do it ourselves, but it's good to understand how it works. So that's how backpropagation happens. That's how you calculate the gradients that you use to update the parameters. Now, the next thing is what really happens, right, when you are updating the parameter. There's something we call an optimizer. Okay. When we're learning a bit of this, we were talking about gradient descent, right? But what I didn't mention then is that the gradient descent is just an algorithm that you use to choose an optimal pathway for your parameters to adjust until it gets to the global minimum, gets the best value, right? That is what gradient descent is. Gradient descent falls under a class or category of um, algorithms that we call optimizers or optimization algorithms, right? And there are many others. But the interesting thing is that a lot of the optimization algorithms are derived from gradient descent. There are a couple of others that are not. So we'll talk about optimizers in more detail later on. But the optimizer is what actually updates the parameters in your neural network, the weights and the biases to minimize the loss. It is not back propagation that updates the parameters. What back propagation does is to calculate the gradients. Back propagation calculates the gradients, and you get the answer from back propagation to say, okay, this is the gradient for this particular parameter for every single parameter in that neural network. Then the optimizers now determine how to update the parameter, right? How to move in the parameter space towards better prediction. It is far more critical in neural networks because of the huge number of parameters involved. If you are talking about basic linear regression, logistic regression, you're probably talking about just two parameters or 10, right? But with neural networks, you're now talking about thousands and millions or even billions of parameters. So it becomes very critical for you to choose algorithms that will move through the shortest path, to the better prediction. So we have different kinds of optimizers. We're going to look at all of them in detail, but we have gradient descent, which we already talked about. Then we have stochastic gradient descent, which is a son, considered as a child of gradient descent. We also have batch gradient descent, which we talked about earlier, right? And then we have mini batch. So stochastic is where you adjust the parameter for every step, for every iteration, for every epoch. Then you have Adam. Adam is adaptive. Um, is stochastic gradient descent. Basically, it's stochastic gradient descent with adaptive momentum, right? That's what Adam means. Um, RMS prop is also comes from it. So RMS prop is a an optimization algorithm that adjusts learning rate. So each parameter has its own learning rate. We'll talk about all of that in detail. So the gradient determines the direction. So here's how it works. The back propagation algorithm calculates the gradient there for every single parameter. Then for each parameter, the gradient tells in which direction the change to the value of that parameter should go. Remember we said for gradient descent, the parameter needs to be updated opposite to the direction of the gradient, right? So if the gradient is positive, you have to reduce. If the gradient is negative, you have to increase. But the optimizer decides the step size. So when we're using basic, gradient descent as the optimizer, we just use learning rate, right? But we have a bunch of other things. But apart from step size, there's what we call momentum, which is um, how much additional change you apply to the step size based on historical data. And we're going to look at all of that. So that's really what an optimizer is. Um, you can see all of that here, right? So you have an input layer, I have hidden layer, I have output layer. Forward propagation is a black arrow, right? Hidden layers has the hidden states, right? You have the weights, okay, and then you have the weights. You have a forward pass. You have activation function of value, you have y hat, you have sigma as your output. Then, when you're doing backward propagation, um, during the feed forward, you calculate loss, you take the loss, right, and you calculate the gradients using back propagation. And then the back propagation gives you the gradients. You now use the gradients to do the weight updates. And the weight updates are determined by the optimizers. So those are kind of the basics. We'll look at optimizers and all of that in more detail in a separate class. So, what is our neural network training look? What does it look like? It's basically forward pass, compute predictions, then compute loss, then backward pass, compute gradients, optimizer step, updates the weights, and you repeat. It is exactly the same thing as what we have been doing. Exactly the same thing, especially when you use something like PyTorch. Of course, if you're writing all of the code, for example, for the backward propagation by yourself, it would have been far, far more complicated than that. But we have all of this tooling, and we're going to get into PyTorch quickly, very soon. So typically, that's what you do. It's still going to be the same thing. Predict from the model, calculate the loss, right? Using a criterion. So PyTorch gives you the capability to choose between different criteria. A criterion is essentially what kind of loss function are you using? That's what PyTorch calls criterion. Then you create an optimizer. Zero grad says zero out all gradients. In other words, do not any previous gradients that had been saved or stored for each parameter, zero it out. We want to start from zero gradients. Then the loss function calculates the loss dot backward. Backward is the backward propagation. That is when the new gradients are calculated. And you can see that the gradients are calculated from the loss function. That's why it is loss dot backwards. Remember, gradient is how each parameter contributes to the overall loss at the output. So after that, when you run loss dot backward, that means all parameters have had their own gradients calculated and stored, saved somewhere, typically in the same neuron or layer, right? And then you run optimizer.step. Optimizer.step now does the actual weight update, right? Does the actual weight update that will change the weights based on the gradient and whatever algorithm that the optimizer has, whether it is SGD, Adam, RMS prop, and whatever parameters you pass with, including learning rate, momentum, and all of that. We'll talk about all of that later. And that's it. So forward pass, which is this first one, okay? It's actually very straightforward, especially when you don't have to think about the maths behind it. The forward pass is this one, right? Compute loss is this one, right? Backward pass. So you do the zero grad because we need to um start with this. So backward pass, you do that. Then you update your weights. 4 steps, but you have to do the zero grad because if not, you will have a situation where the new gradients will be added to the existing gradients and your model will be messed up. Okay, that's it. So training is iterative improvement. Forward pass is prediction, right? That's forward propagation. Predict. Loss is evaluation, calculating. So we'll use a criterion, mean square error, binary cross entropy, categorical cross entropy, and all whatnot. Backprop plus optimizer is updating the weights. And you keep repeating this for any number of epochs, right? Now, one interesting thing you see here is that this is batched. You have a batch thing here. So where you have a lot of data, you may not load all the data at once into your model to train. It's going to take a long time and it's not going to be optimal. So you take your data and you set it into batches. So there's a pipeline that allows you to batch data. Okay. And as usual, the other thing you remember to do is to add different um you do your train test split and that's it. So that's the training loop. This is basically a repetition of the same thing. Um, we are going to, yeah, this is kind of a summary of it, right? Perceptron, single linear decision, hidden layers, then forward propagation for computing predictions, loss functions for measuring errors, back propagation for computing gradients, optimizers for updating weights. So a neural network is just a sequence of linear and nonlinear transformations. Okay. Okay. Right. So we are going to take an introduction into PyTorch. We are going to continue with PyTorch. Yes, so PyTorch um, really helps. PyTorch is a very, very useful, helpful tool because all of those maths that we saw in just a few slides ago, all of that back propagation, all of that, with PyTorch, you will not even know that that kind of maths even exists. We'll be doing a lot of really interesting stuff, right? By the way, before PyTorch, right, even though we are using PyTorch here, there were a bunch of other tools that you could use for training neural networks. TensorFlow is was like the first, but these days TensorFlow has is getting retired, I would say. TensorFlow was built by Google and it's getting retired and replaced with something that is more approachable because it's a bit more difficult to use, right? Even though a bunch of different layers were brought on to make it easier to use, but it's still not. In fact, PyTorch has essentially been has taken over because uh, it has been so easy to use. So we are going to use PyTorch for the rest of this class, for the rest of this course to train and build neural networks. So we'll start by just learning how to use it. Yeah, so it's open source. That's the first thing. Um, you don't have to pay for it. Of course, almost all the neural network, machine learning training frameworks are free of charge. I don't know of anyone. Well, there used to be a bunch of proprietary ones in those days, right? Like Touch. PyTorch actually came from Touch, which was written in C++ language. But they ported it to Python and they call it PyTorch. But I don't think people even use Touch anymore. And then there are a bunch of others as well, right? So PyTorch is used for building and training AI models. It just follows a standard Python API. So it's very easy to use, it's flexible, and it uses what we call a dynamic computational graph. So if you actually took note of what I was saying about the backward propagation and back propagation algorithm, you see that the best way to achieve that is using what we call a computational graph. And this is an advanced topic in maths. But once you are able to state everything as as a graph, computations as graphs, it is easy to traverse graph and do the necessary calculations and computations without having to in fact the study of graph modeling and graph models is an entire study in computer science. So anyway, it has a dynamic computational graph. What that means effectively is that the computational graph is built at runtime as it is reading your code. As it is reading the code that you wrote, it is building the computational graph. This is in contrast to something like TensorFlow, which has a static computational graph. For TensorFlow, it will first of all read your entire code, then compile. So you have to have a compile statement at the end of your code that will compile your computational graph, and then you use the computational graph, right? So, it's very popular for both research and even now, these days, production deployment for computer vision, natural language processing. Like I said the graph is built on the fly during execution as it is running your code, is building the computational graph. And like I said, the computational graph is just a representation of the mathematical operations in your model, right? But it's represented using a graph data structure. So it also is Pythonic in a way. So control flow, like if statements, for loops, recursion works naturally. You just write it as natural Python expressions, statements, and functions, right? And it interprets it into the graph. Unlike some other things like maybe TensorFlow, where you would have to um, there's a special way you have to write things like branches, if statements, loops, and so on. Okay. So again, ideal for research custom models for debugging complex logic. So like I said, TensorFlow has a static graph. While PyTorch you define, you run your Python code is the graph. It's research friendly, it's Pythonic, it has an intuitive API. You can easily debug with the standard tools like printing. With TensorFlow, it's not easy to print stuff. You have to, I can't even remember how I used to print stuff with TensorFlow. I think you have to extract it. You have to have a variable in your graph that will pull the data or that you will store the data that you want to inspect. And then after you have finished running the graph, you go back and extract that data and you expect it was basically, in fact, probably is one of the reasons why TensorFlow is being retired, this static graph and how difficult it is to use to debug, to fine tuning and so on. Right. But yeah. So academic research, rapid prototyping and all of that. PyTorch actually came from Touch. Touch came from Meta, from Facebook. And it's being used by a bunch of other companies, including Tesla, OpenAI, Microsoft. It's also a backbone for a bunch of AI companies now, like Hugging Face. The Hugging Face transformers, PyTorch Lightning. PyTorch Lightning is another framework built on top of PyTorch that simplifies training of models, stable diffusion, and so on. So it's easy for you to seamlessly transition from just research you may be doing on your models to production. Okay. So that's some of PyTorch. Some of the key features that you see, tensors. Tensors basically are a fundamental data structure in PyTorch. So when you hear tensors in machine learning, we are effectively referring to a multidimensional array, similar to NumPy arrays, right? Generally, if you look at it, the way we characterize data structures for mathematical modeling, is we call single numbers like 1, 2, 3, single numbers, we call them scalars, right? Then numbers that are single dimensional, one dimensional. A single number is zero dimensional, it doesn't have any dimension. But a number that is one dimensional, like a list of numbers, like we're talking about embeddings, we've been using a terminology, vectors and so on. Yeah, a vector is a one-dimensional um, tensor, basically one-dimensional data structure. A matrix is two-dimensional. As you can see, a matrix has rows and columns. That's why it's two-dimensional. A vector has only a single dimension, just a row or a column, irrespective of what it is. Then a three-dimensional data structure is called a tensor. Well, to be more precise, all of those are tensors. A scalar is a tensor, a vector is a tensor, a matrix is a tensor, right? So a tensor is a general name, a generic name for any multidimensional data structure, right? It's just that we have specific names for the one-dimensional one, which we call, vectors, and two-dimensional, which we call matrices. But beyond the second dimension, we don't have any special names for them, so we just call them tensors. So that's one thing to remember. The other interesting thing is that PyTorch allows you to move tensors, across devices. And this is based on the underlying infrastructure of how GPUs, CPUs do computations. You actually have to have the data on the GPU, right? If you are moving data from CPU to GPU to do computation, it will be too slow. So data has to be stored in the GPU so that it will compute faster, right? And GPUs give you much faster computation. So that's tensors. Then you have what we call autograd. So remember we talked about backpropagation and the chain rule. And the main elements of the chain rule is differentiation, right? It's a gradient. You need to calculate gradients of everything, you know, for you to be able to do back propagation. You cannot do back propagation without calculating gradients. In the old days, before PyTorch, even with the likes of TensorFlow, we were calculating gradients manually. Each time you build a network, you will have to also manually write the gradient function for it, right? But with PyTorch, effectively every function you can use in PyTorch, a gradient function has been written for it, right, as well. So um, you can you hardly ever have to write your own gradient functions, right? That's what we call autograd. Autograd is a module that automatically calculates gradients of any operation that you perform on the tensor, whether it's addition, subtraction, division, whether it's even an if statement. If statements even have gradients that can be calculated. Sine, cosine, exponential, um, square roots, all powers, logs, logarithms, anything that you do, even step functions, even piecewise functions have some kind of gradient. So effectively, what this means is that you only need to do half of the work, which is to define forward, the forward propagation. Right? The backward propagation is part of your definition of the forward propagation, as long as you're using PyTorch's built-in functions to build up your forward propagation, right? And it is very, very crucial, right? Because the back propagation, that's what you're using to train the neural networks. So if you don't have gradients, you cannot train. We've already seen that. That's what you use to adjust your model parameters. Then the PyTorch also has dynamic computation graph, like I mentioned already. So as you are running your training code or your model building code, the computational graph is being built as the code is executed, right? So that simplifies debugging because it means you can just jump in and um, change things at any point and rerun the code instead of having to recompile the computational graph. Okay. And it also allows for more flexible architectures because it means you can build architectures that are, dynamic. They can change during runtime and it will still work. But with static graphs where you have to compile, you could not change the architecture after compilation, right? Then PyTorch has a touch.nn module. So this is a module that contains all of the building blocks that you need for building neural networks, including a wide array of different types of layers. We're going to talk about layers later on, the types of array of layers rather. We've talked about um, you know um, fully connected or dense layers, but that's not all. There's a whole bunch more. Okay, so you typically will build a model as a Python class that inherits from the touch.nn module or nn dot module, which is um, a class that you can inherit from. The other thing that PyTorch does for you is it gives you data sets and data loaders. So you can easily load data sets and use them for training, especially if you are learning, where you are looking for data to learn. So remember, when we're using sklearn, we also used a lot of sklearn's built-in data sets. So PyTorch also has built-in data sets. You can get them from touch.utils or data. And that the pipelines, the data loaders streamline the process of loading and batching data. We're going to look at how to use that. Then PyTorch also has GPU acceleration. It has built-in support for GPUs using the CUDA. Okay. And CUDA is a specific kind of library that was built by NVIDIA for people to easily program the GPUs that they manufacture. But it has become really popular. And what has happened is that a lot of almost every software, every machine learning um, training framework has CUDA integration. So you don't have to write the CUDA code yourself. You just write the same code as you would have written for a CPU, and the framework is going to compile it for CUDA and use it for CUDA, which is quite very, very helpful. Um, yeah, so that's it. So these are examples of what you could do with PyTorch. So for example, for a neuron, you would use nn.linear, which is just a layer, a single layer that has any number of neurons. You specify the number of neurons when you are defining a layer. So NN linear is the base for defining layers in Torch, in PyTorch. Then you have activation functions. So you also have different activation functions. We are going to talk about that a bit more in detail. You have NN or ReLU as an example. We already kind of looked through some of them, right? But we're going to go into more detail on the activation functions. Then forward propagation. So for propagation, we used to do model dot with sklearn you do yeah, just do model, right? With sklearn. And it's the same thing here. You just call the model, you create the model, and the model is a callable. Even though it's a class, it's an instance class, but you can just call it like a function and pass X, which is the input from your data, and it will predict and give you a predict. Then you can define different loss functions in product that are called criterion. Okay, and there are many of them. This is binary cross entropy loss, BCE loss, which we use for logistic regression that time. We always use BCE whenever you are doing classification of binary um, um, categories or binary classes. Then if you want to do the gradient descent, the optimization phase of your training, you just use optimizer dot. If you want to do back propagation, which is the calculation of the gradients itself, use loss dot backward. So yeah, so let's talk a bit about tensors. Like I said, a tensor is a multi-dimensional array, right? And it's a core data structure in PyTorch. It is very, very important to understand tensors, right? Tensors are a generalization of all data structures. So for a zero-dimensional data structure, we call them scalars. That is a number, right? Like 0, 1, 10, 15.5, 0.62, whatever number you can think of, that's just a single number, right? Vector is a one-dimensional data structure basically represented as an array of numbers, an array of numbers. While the matrix is a two-dimensional data structure, which is a matrix of numbers. It has rows and columns. And then once you go beyond the second dimension, go to three-dimensional and above to n-dimensional, you now higher dimensional arrays. Like I said, those don't have names. So we just call them tensors. But all of them are tensors, right? So one thing with PyTorch is it's very similar to NumPy. Okay, if you take a tensor in NumPy, you can get the shape. The shape will tell you the number of dimensions in that um, tensor. So if you take a zero-dimensional um, tensor and you try to get a shape, you're going to get an empty um, tuple. It's basically empty that it doesn't have a dimension. But if you take a one-dimensional vector, one-dimensional tensor, which is a vector, and you try to get the shape, you're going to get a single number, which represents the number of, um, the size of that dimension, basically the number of numbers that can fit into that vector, right? Then, if it's two-dimensional matrix, you are going to get two numbers. The first one is the number of rows, and then the second is the number of columns. Okay. Then if you take anything more than that, it will give you always a list of numbers, right? If it is a three-dimensional tensor, it's going to give you a list of three numbers, and the three numbers represent the X, Y, Z, the row, column, and depth, or something like that, right? So tensors have that shape. That's what shape means. Then D type is the data type, which means it can be an integer, it can be a floating point number, right? Those are the two main ones. Others like strings and so on don't really exist in PyTorch because PyTorch is designed to deal with just numbers. Unlike others like NumPy and maybe Pandas, which can you can deal with letters and words and things like that, or objects. But by the time you get to a tensor, you have to essentially change it to numbers. But those numbers have types. So you have um, floating point numbers, and the floating point numbers have different sizes. So you can have 32-bit, you can have 64-bit, you can have 16-bit, you can have 8-bit, you can have 4-bit. Those are all the sizes. Then you can have integers also that have different sizes. So you can have again 64-bit integer, 128-bit integer, 32-bit integer, 16-bit integer, 8-bit integer, and 4-bit integers. So those are the types. It has to do with size and partition. Broadcasting is something special. It's just a property where you can use a tensor that is has less dimensions and still use it in operation with another tensor that has more dimensions, as long as the dimension on which you are doing the operation is the same size for both. Again, I'll explain that in detail. Yeah, you can easily create a PyTorch tensor from a NumPy ND array by just calling PyTorch tensor, right? The constructor. We are going to see examples shortly. Then the other thing, like I say, GPU acceleration, the tensors, you can specify where the tensors should be residing in, whether they should be in the CPU or in the, or you use what we call to. This to is a keyword in PyTorch to say, okay, move this variable into CUDA. If you are saying move this variable into CUDA, you're going to move that variable into the GPU, right? But not just into the GPU. The code that is all the code that you write to manipulate variable will be ported into the CUDA language. So, but you are doing it, you don't really know what's going on because it's happening all under the hood. And CUDA gives you massive speed up, massive acceleration. If you use a GPU, we are going to see it very soon when we start training models, these more complex models with your Colab notebook. You train a model with a CPU, it will take you 5 days. But you train the same model with a GPU and it take you 5 minutes. That's when you understand, well, okay, maybe that's a bit of an exaggeration, but it really is, that's how powerful GPUs are. Yeah, so so has this already mentioned the shape and the data type, D type. The device is which device you moved it to, right? Where it is residing in. Requires grad is another property, which means requires grad means when the back propagation algorithm is calculating gradients, this tensor should also have its own gradient calculated, right? That's what requires grad means. If requires grad is true, that tensor will have its gradient calculated. But if requires grad is false, that tensor will not have its gradient calculated. And if you ask yourself, why would there ever be situations where I don't need to calculate gradient? Yes, because sometimes if you're using your model for inference, you're not training it, you don't need to do any backward propagation, so you don't need to calculate gradients. Same thing with if you're doing evaluation of the model, you're not training it. So if you're not training models, you really don't require to calculate gradients. Yeah. So this is an example of how you can create a tensor from Torch. You use torch.tensor. Import Torch, you use torch.tensor, and you can specify the tensor itself. So let's look at the different ones I mentioned. A scalar, you can see this number one just has a single value, and this is how it's represented, right? A vector, you can see it's a list, a single list. It has one direction, only one dimension, right? Whether it's column wise like this or row wise, it's still a vector. This is row vector 537. Shape is 1 by 3, but it's still a row vector. This is a column vector, shape 3 by 1. It's still that. But typically in vectors, you don't differentiate between row, whether it's a row or column vector in PyTorch. A vector is just a vector. And I'll show you how it is represented. Then a matrix is a two-dimensional data set. It has rows and columns, rows and columns. Then a tensor is three-dimensional. So graphically, you can represent it as a cube, right? But this is a three-dimensional tensor. They can be multiple dimensions. So four-dimensional, we cannot represent it graphically anymore because it becomes more difficult. Five-dimensional, it cannot represent it anymore, right? At this point. So, but here is another way of representing it where you now have rows and columns and units inside. So PyTorch tensors are like NumPy, but they are pure aware and they can do autograd. So this is a very simple way for you to define a simple neural network in PyTorch. Like we said before, you use the module class as the base class, as the parent class. Okay. And then you define an initialization function where you can specify um, the architecture, right? And then you define a forward function where you can specify the forward pass calculations. You don't need to do a backward function because in this case, it is actually using autograd will automatically calculate gradients, and then backprop will automatically do the backward propagation. So module class is the base class for all neural networks. It is what manages your parameters, layers, and placement in device. So whatever you do to this single module will happen to all the parameters. So for example, if you move this module um, to the CUDA device, all the parameters will move as well. All the tensors that make up the parameter will move. Okay. Um, if you um, set this entire module as requiring grad, that is, it needs to be calculated. Its gradient needs to be calculated. All the parameters will also adjust in that way. And you have so many different kinds of layers, which we'll talk about some of them. We'll be using some of them as we move forward. So we have common layers like linear layer. So whenever we see nn.linear, that is the fully connected layer, the dense layer, like I said, where all the inputs are connected to all the outputs, right? Every output is connected to every input. Then you have layers that are basically just activation functions, right? Like the ReLU layer is a whole layer. It's considered layer, but it's not a layer in the sense of what we're talking about when we're saying layers are neural networks, because layers actually are neural networks. But in PyTorch, they have created that construct of activation functions being layers. So you can look at them that way, but they're not really layers in that sense. You normally append them to a linear layer, right, to form a linear layer with a particular activation. And the reason why it's separate is so that it gives you flexibility. You don't have to have, you don't need to couple the activation function with the type of layer. Then you have other kinds of layers, which you talk about when we talk about architectures. The conv2D is a convolutional neural network. That's a basic layer of a convolutional neural network. It's a two-dimensional convolutional layer. Then the LSTM is a long short-term memory, which is a recurrent neural network or sequence network. Again, we'll talk about those. So PyTorch allows you to easily build all of these primitives. They're not really primitives per se because these are really complex stuff. Doing a convolution is a really complex thing, but Python just condenses all of it into a single command and it becomes a primitive in that sense, right? So then you have to define the forward method. So four methods where you implement your own specific approach of how the signal is passed from the input to the output. So remember, we said the signal in a feed-forward network, signal always goes from the input across the different layers to the output. That's what the forward method basically defines. It gives you the power to define it as you want. So define how data flows through the network. When you create a model and define a forward method, then you can just create an instance of that like this model equals simple net. Then you pass the input as a as an argument, and you call the model as if it were a function. And this will under the hood internally we'll call this forward um method and do relations, and the output you get will be the prediction that you get from your model, right? So the things that PyTorch will handle for you automatically when you use this simple approach is one, parameter registration. You're going to register a parameter with the PyTorch runtime, right? Um, Especially for things like autograd and so on. Gradient tracking, right? Which is the autograd that we talked about. So you can track your gradient. And then backpropagation, which happens when you're training the model. So all you need to worry about when you're using PyTorch is your model architecture, the structure and the flow. You don't need to think about the mathematics of it anymore. You don't need to think about gradients, calculation, back propagation, the whole mechanics of training. PyTorch will handle it, right? So it takes away that whole, that will take that problems away from you. So you focus on what really matters, which is what model architecture should I be using? Okay. So when you get into neural networks, you find that when you are into neural networks, it's really more about model architecture, nothing else. It's really about model architecture. Okay. Well, there are other things. Yes, there's optimization, there's evaluation, there's things like regularization, the techniques that you use to improve the accuracy of your models and stability and so on. But those are now um training related, model architectural related, you know, ideas, mechanics, not how do I code this, code that. And that's why I've always said that machine learning is not about programming. It's not a programming course. It's not about how well you can write code, right? It is more about how well you can train a model. Okay. So AutoGrad, what is AutoGrad? AutoGrad, like we said, is the automatic differentiation engine in PyTorch. Basically, automatic gradient. That's what it is, right? So what AutoGrad does is that for all the tensors that are registered, right, either by manually registering them if you're creating the tensor manually, or automatically registered by the nn.module class if you create a layer based on that in the module class, it always automatically records or registers the parameters, for that layer. So what AutoGrad does is it tracks operations on those tensors and it builds a computation graph automatically. So the computation graph is building is both the forward graph and the backward graph. The forward graph is for the forward propagation, the forward calculation of the predicted output, right? Or that will lead to the predicted output. Then the backward graph is what is used to calculate the gradient, right? And that's what it uses to automatically calculate gradients when you call loss.backward. So that's what AutoGrad does. And it is very, very, very powerful because again, it takes a lot of cognitive load away from us who are using this framework. We don't need to do manual calculation for gradients or derivatives, which some frameworks will demand or require that you do. You have to calculate it. But you don't have to. And then it also enables propagation, right? Because autograd calculates gradients, so back propagation will happen. It also enables gradient-based optimization. So if you want to do optimization based on gradient, and of course the deep neural networks, because again, remember gradients in deep neural networks are chain rule. Chain rule is really complex to do, and sometimes you can get it wrong, right? Then the dot backward is a method in the criterion class. So every loss function, you can call this dot backward. And what it does is compute the gradient of all of the output. That is the gradient of the loss at the output, not in between, at the output, with respect to all tensors that have registered they want their gradient to be calculated, right? And you register that you want your gradient to be calculated by specifying requires grad equals true. Right. And then those gradients that it calculates are stored in a property called grad. So it's actually very easy for you to say gradients. Note that the gradients are still actually numbers, they calculated gradients. It's not the formulas for calculating them. The formulas are part of the framework, right? And that's how he's able to do that. Then the interesting thing is that after that backward, right, um, the computation graph that was created is discarded unless you explicitly retain it, but it's discarded after backward is called, right? So the computation graph supports dynamic model structures, like we said already, because it's dynamic computation graph, it builds up in real time, eh, you know, just in time as the code is running. Okay. So yeah. So AutoGraph automatically apply the chain rule behind the scenes. Okay, so that's it. We would have had a hands-on, but this is a way too late. We are going to do a walkthrough on PyTorch and how we can use PyTorch to do a bunch of things when we meet next week. So this week was mostly on the theory, right, of you know, neural networks and all of that. But we're going to do a little bit of walkthrough next week. And then we'll also look at optimization and training dynamics. So understand optimization. That's also a whole lot of stuff. So it's going to be really jam-packed. That's all from me. I hope you enjoyed it today. Are there any questions?